Hello everyone, welcome to the second part of the video that is focused on the trustworthy systems on our Catalyst 9000 series switches. To understand the different embedded trustworthy technologies, let's go over the basic security blocks in a switch. Let's start with the firmware and processor. We need to start trust from the hardware layer. The underlying hardware needs to be trusted before any software can run on it. How do you know for sure that a switch in your network has not been altered since you deployed it? So with the ability to use zero-touch provisioning and plug-and-play services to configure remote network devices, switches can now be shipped directly to a branch office site, powered on by a non-technical employee and remotely configured by an IT expert from a cloud management portal. But between manufacturing, warehousing, shipping, and installation, how do you know that the IT device has not been altered in any way? So being able to challenge your switch to be able to prove its unique identity is something that would be ideal, right? And so that's what's going to entail the hardware integrity portion of the trustworthy systems. To provide a strong root of trust, the Cat9K switches incorporates a tamper-resistant chip in its hardware at manufacturing. It's called the Trust Anchor Module or TAM chip. The hardware trust anchor module primarily provides multiple trustworthy functions, which I'm going to go into detail. So first, it provides an immutable identity. The secure unique device identifier, which is the SUDI, that gets programmed inside the trust anchor module and manufacturing, provides a unique device identity and serial number for the switch. The switch can be cryptographically challenged at any time during its operational lifetime to validate its identity. This way, customers can ensure that they are still talking to the same switch that was deployed in their network months or even years ago. The SUDI certificate is changed to a publicly identifiable root certificate authority, and its entire certificate chain and keys are stored in a tamper-resistant chip. So next we have the secure boot. So the immutable hardware, which is a TAM, is needed for the secure boot process, and this is what will validate the bootloader, which will initiate the boot process. The TAM protects the first code of all instructions that are run by the system when starting up, and it protects it from compromise. Some network vendors try to build their secure boot from the BIOS instead of a secure hardware anchor, but once the BIOS itself is corrupted, the attackers now own the device pretty much, and so the corrupted BIOS can now maybe instruct the switch to load an incorrupt operation system. So it's really important to be able to have a secure boot process, which Cisco does have in place. Now, having a strong random number generation is at the core of encryption, and having a weak RNG undermines the entire encryption system. So random number generators play a key role in creating cryptographic keys and establishing highly secure communications between users and websites. Without assured randomness, an attacker can predict what the system will generate and undermine the algorithm. The Cisco Trust Anchor module is compliant with the NIST and provides a certifiable RNG that extracts entropy from a true random source within the Trust Anchor module chip. Finally, the Cisco Trust Anchor module provides a highly secure storage for keys, passwords, customer credentials, and other critical security information for the device. The chip can store about 50 kilobytes of host data in a physically tamper-protected manner. So now we have a root of trust that cannot be tampered with, which is the TAM chip. It sets the precedence for our trustworthy systems. What if now we could provide a secure mechanism to detect if the software that is now running has been tampered with during boot time? And this brings us into the boot integrity. The image verification feature allows users to automatically verify the integrity of Cisco iOS images and ensure that customers are confident that the software running within their system is secure and has not been tampered with. Because a production image undergoes a sequence of transfers before it is copied into the memory of the switch, the integrity of the image is at risk every time a transfer occurs. To make a downloadable image trustworthy, it can be protected with a cryptographic hash function that ensures that no one can modify your software without someone noticing. The hashing is done on the original IOXT code with a SHA-512. The hash output is then encrypted with a private key to create the digital signature, and that is combined with the software image as a digital signature package. That image is then downloaded directly to the customer's devices, which use a matching public key to decrypt the hash output and image package to verify that nothing has been altered from the original image. Only software images that pass this critical test can be loaded on devices, preventing any malicious code from booting. On the Switch CLI, the file verify auto command enables image verification globally. So all images that are to be copied via the copy command or by reloading are automatically verified. So although both the copy and reload commands have a /verify keyword that enables image verification, you must issue the keyword each time you want to copy or reload an image. The file verify auto command enables image verification by default, so you no longer have to specify image verification multiple times, and so you can choose between the two which one suits you best. Let's take a look at the output of image signing on a Catalyst 9200L switch. So after the file verify auto command is issued for global verification, the switch is then reloaded. We see the output saying verifying file integrity of the iOS to be booted. After some time, we can see the CLI output of the embedded hash and the computed hash, which match, so showing that the digital signature is successfully verified. So what an embedded hash is that it's a hash that is stored by Cisco in a section of the Cisco iOS image during the image build process. And the computed hash is the hash that the image verification feature then calculates for certain sections of the Cisco iOS software image file when the verify command is executed. I spoke about persistent threats being the malware that can maintain a presence on the switch despite multiple reloads, right? So it consists of malicious code that places itself into the very root of software. So even a power reboot or reset cannot remove that code if there's no hardware root of trust to detect and keep that code from running. Cisco Secure Boot is a secure setup process that your Cisco device performs each time it boots up. Cisco is differentiated from our competitors by anchoring the secure boot process in the hardware, and so it provides the most robust security since the hardware modification is very difficult. It's very expensive, and it cannot easily conceal even if hackers have the physical possession of the device. So each piece of code in the boot process measures and checks the signature of the next stage of the boot process before the software boots. So to start with the first instructions that run on the CPU are stored in the immutable hardware, which is the TAM chip. That will validate the integrity of the microloader and make sure that there has been no tampering done to it. After the device is powered on, the microloader will now verify the bootloader code, which is responsible for installing the OS binaries by validating the Cisco digital signature on that set of instructions. The bootloader would then validate the operating system and check to see if it's from Cisco by checking whether it is digitally signed by Cisco. The operating system is then launched if all the checks are passed. If any of the digital signatures fail, Cisco will not let that software boot on the device, and that prevents malicious code from running on the device. When the Cisco hardware anchored secure boot authenticates the software as a genuine Cisco device with the TAM chip, the operating system will then query the TAM chip and ask it to verify whether the hardware is authentic. And it verifies by cryptographically checking the TAM for a secure unique device identifier that comes only from Cisco. And with step 5 and 6, it depicts like the usability of capabilities for the runtime defenses, which I'm going to get into later on. So here you see a ROM1 secure boot verification, and then we also see an iOS boot verification as well. Okay, so now that we have the switch successfully booted up and running, what are some of the things we can do to make sure that during the time of runtime, we reduce to nothing attacks from hackers that compromise and persist within critical infrastructure devices? It is very critical to establish and maintain trust within the network infrastructure devices at all points during the system runtime. So that's what runtime defenses are pretty much. They protect against the injection of malicious code into running network software, making it very difficult for attackers to exploit known vulnerabilities in software and hardware configurations. So after the secure boot process and having the switch in runtime, we can run a command to display certain details about the operating system that is currently running on the system. So I spoke on how there can be some injections to the in-memory copy of the iOS code. So we can compare values to ensure that there haven't been any tampering. Administrators can now use the show software authenticity running command to verify that the authenticity of the image that is currently booted and in use on the device. It's to verify that it's integrable. Administrators can verify the authenticity and integrity of the operating system image file in Flash by using the show software authenticity file command. So now administrators should verify that the certificate serial number, which I have highlighted here, matches the value obtained by using the show software authenticity file of the image file in Flash, since the file in Flash cannot be modified, but the one in memory copy can be modified. So you can compare those two values to make sure that it's the same, and that's a good indication of no tampering to the operating system. Okay, now let's get into some runtime defenses. So ASLR is a defense that initiates before the OS even loads. It randomizes portions of a device's memory layouts using fuzzy logic algorithms, preventing an attacker from designing malware that depends on a known memory arrangement. So for example, every Cisco Catalyst switch of the same type is configured with the same memory layout when powering up. So when you power up the switch, the ASLR kicks in and randomizes a portion of the memory, and this results in each switch having a different running memory configuration. An attack designed to use the factory memory layout or a memory layout on an attacker's device will be stopped since the memory layout changes. Since the memory layout changes, then creating an attack based on that becomes very difficult, pretty much. We have the X-base, which is frequently supported by a CPU maker's architecture and prevents executable code that is hidden in data streams from executing in memory spaces. So when you enforce X-base in network devices, it marks memory regions as non-executable so that malicious code hidden in packets cannot be executed in those memory regions, which adds another layer of protection. Built-in object size checking and safe CLs, also two runtime defenses that work together to manage how incoming data is copied into memory. So an attack that relies on forcing a larger amount of malicious code via a routing packet, let's say a CLI command, into a smaller chunk of memory to cause a buffer overflow is stopped by implementing the BOSC in combination with a compatible compiler technology. So finally, I'll get into the boot integrity visibility that allows Cisco platform identity and software integrity information to be visible and actionable. So during the boot process, the software creates a checksum record of each stage of the bootloader activities. You can retrieve this record and compare it with a Cisco certified record to verify if your software image is genuine. If the checksum values do not match, you may be running a software image that is either not certified by Cisco or has been altered by an unauthorized party. So here you can see the show platform SUDI certificate. This is what will display the checksum record for the specific SUDI from TAM. And then when you do that, you're going to get 3 certificates. So the third certificate is something that you can use the OpenSSL command to extract the device page serial number that has been encoded into the switch. And then you can also run a show var to know what the model number and the system serial number is of the switch you have right now. And when you compare those two and they match, then you know that you have the correct device with you. But then if they do not match, then you know that this is a counterfeit device that you're using. So these are pretty much the key features that are developed by the Trustworthy systems. We have the image signing and secure boot that protects against compromising software and boot code. We have the SUDI and the Trust Anchor that protect against counterfeit hardware. We have the runtime defenses that protect against the running software, attacks on the running software. And we have the integrity verification, which helps us to visualize our trust, which is very, very important. So I'll end the session with the feature support on the platform. So on a Catalyst 9000, all these features I've spoken to you about are supported on each and every Catalyst 9000 switch that we have. On our legacy platforms, we do have some gaps. Here you can see, I'll just leave this on so you can see where the gaps are. So I have some resources page here. If you want to know more about Trustworthy, you can go to the trustportal.cisco.com and it will give you more information, or you can reach out to me directly. Thank you so much for being here with me for this session, and have a great day. Thank you.